Good evening to Indian Space Lab and Mr. Sandeep Khare. Probably I believe he's joined. And my dear students, my dear boys and girls, today we are going to speak about launch vehicles and spacecraft systems. In fact, we will be touching spacecraft systems, not to the, at least some orbital things and all we'll touch. And it's an overview. So you will get an overview means you will get an idea about it, how things are going on. So you can see the first slide shows the first 4 rockets launch. You can see the year, 1961. Okay, probably before all of us are born. So one is the Vostok USSR. So how technology has been developed. You see the vehicle. Still, you can see the same principle is used by SpaceX also. There's clustering of engines. These were semi-cryo engines, and probably is using a locksmith or something like that. Okay. So then came the Mercury Redstone of US and Mercury Atlas and Gemini Titan. Okay. These were them in the 60s. So where India's space journey? India's space journey, let us start with a small video of LVM3, that's Chandrayaan-3. So what you're seeing is the historic launch of Chandrayaan-3. And if you look at the launch vehicle very carefully, the launch, you can see before launch, certain things are moving apart from the launch pad. In fact, what are those things? In fact, there are certain umbilical connections. There are some cable connections will be there. For example, we are in the payload fairing, the topmost portion where the Chandrayaan-3 is sitting, or any spacecraft or any passenger is sitting. According to us, it is a payload. Okay. That is to be continuously cooled. So we'll be supplying continuous cooling through that payload fairing. So those connections are called umbilical connections. It is getting detached. Similarly, power connections will be there. Many things will be there. So those getting things are separated. And also you can see some metallic things is moving apart. That's cryo amps. So then only the launch taking place. And when the launch taking place, as he was telling, it is so 2 S200 motors are there on either side of the core vehicle. So we call the core vehicle. And on either side, what you're seeing, the strap-on boosters. It is similar to our Ariane configuration. This is 200. That is 200 tons of propellant. So that is S200. And that is PP and PM. That is P plus and P minus only. That is pitch minus and pitch. That is a location. Pitch, yaw, and roll are the 3 axes. So pitch, the pitch side of the vehicle, P minus and P plus. These 2 boosters are kept. And you can see the first boosters are separated. Subsequently, he is announcing about L110 stage. That is a liquid stage. L means L stands for liquid. Then finally, the cryogenic stage, those things are, it was cut because of saving time. And finally, our spacecraft payload is released to the, to its path. It will take its own. It has got its own engines. So it will be taken by its own thrusters to the relevant orbit. It has got separate engines. Thrusters are available. So our objective is to put it in the specific orbit. So this is only a glimpse of our history, but whole history is not here. 63, we have the first launch, and 69, the formation of ISRO. And of course, thanks to Dr. Vikram Sarabhai. And 75, the launch of Aryabhatta. And again, the satellite SLV3. But again, here ASLV missions are not shown here, and also PSLV in 1992 or so. That's also not shown here. Then LVM3 is 2014. Whatever we have seen, there was an next mission called, that's with a mission without a cryo stage. It was happened in 2014, and the actual mission was in 2017. Okay, now the Chandrayaan-3 was in 2023. This is only our Sriharikota. It is our original spaceport. In this figure, you can we can see there are 2 buildings, 2 tall buildings. The one which is closer to eye is the first launch pad, and one which is far away is the second launch pad. Okay, it's also called a vehicle assembly bay, VAB. In VAB, what's happening is the vehicle will be assembled and the vehicle moves out. Whereas in the first launch pad, the vehicle will be assembled and the launch pad is moving out, not the vehicle. Vehicle will be stationary at that location. The second case, the vehicle will move out, the building will be there. There is a difference between these two, FLP and SLP. First launch pad and second launch pad. This is the control center. And of course, probably this is a historical event. Why it is a historical event? Now you see the Sriharikota is our launch, present first launch spot, or current launch spot. Recently, we are going to, we have started, it has not become operational. It is in the Kulashekara Pattanam. That's in the Thoothukudi district of Tamil Nadu. But the advantage of, obviously, you can see the advantage of Kulashekara Pattanam. When a launch vehicle is considering, as far as the launch vehicle efficiencies depends upon the energy it spent to take its payload to a specified orbit. In that context, you can see the Sriharikota starting vehicle has to take a turn around Sri Lanka. The landmass is there. I'll show you one more figure later. You'll be seeing how much of landmass is on that side. Whereas in this case, it is straight away going. Okay, so we can save so much of energy and take more payload with the same vehicle. The same vehicle is used. You can take it to more payload. This is only a test center in ISRO Propulsion Research Center, where our liquid engine, cryogenic engine, and future NGLV, new generation LOX methane engine, will be tested. This is also near Tirunelveli. This is one engine test. Now coming to our launch vehicles of ISRO. First one is SLV3. Probably you may be knowing the team leader or the project director of SLV3, none other than Dr. APJ Abdul Kalam, our ex-honorable Vice President of India. He was the SLV3 project director. And ASLV, in fact, it was something like a test vehicle because you can see the strap-ons. The strap-on separation, everything we have learned by using ASLV vehicle. And later, PSLV, we have used all those technologies on all the experience we gathered from ASLV, separation and other things. Okay. So PSLV is having multiple versions are there, and you can see the payload mass also 1,860 kilogram. In fact, it started with 1,000 kilogram. Then years of improvement in propulsion system and other things. We have, the efficiency of the engines and all. It has become 1860. And now currently Mark II and Mark III is our major workhorse. And it can take a payload mass is now shown here is 4,000 kilogram, but it can go up to 5,000 kilogram now because of modification. And this vehicle we are used for all Chandrayaan 3 and Chandrayaan 2 and 3, and is going to be used for Gaganyaan also. Space missions, human-rated missions, the entire vehicle is under modification. Improving the reliability part of it. Now we are coming to model rocketry. Model rocketry, why I'm going to talk to you about model rocketry is because students like you will learn a lot of things using this model rocketry experiment. And also in space, I represent InSpace now. Currently, I'm working for InSpace. For the first time in the history of InSpace or in India, we have conducted a model rocketry experiment. It's like what do you call it? For the students, it is a competition. It was in Kushinagar near Gorakhpur, UP. And maybe around 50 to 60 institutions have participated, including IIT and IITs and other engineering colleges. And the students will be learning a lot about model rocketry. You can see the vehicle itself, a small rocket itself. It's hardly around 1.5 meters or 2 only. But still you can see the fins and the top the payload fairing or the nose cone. Here we can say it's a nose cone, then the body tube, and bottom side the nozzle. And this is this figure doesn't belong to India. It's from from the net I have taken. Okay, you'll see how the performance, and also we can see the major elements separating and the retrieval also. There are major 2 parts of the experiment. One is the retrieval of the CANSAT, and second one, the retrieval of the body. Okay, and in our case, we are retrieving the nose cone also. This is our experiment, and in fact, we have a separate test. Competition is for CANSAT alone. In that case, the rocket will be supplied by InSpace team, and you have to make the universities or institutions have to make the students have to make the CANSAT, bring it, and we will give the rocket, and you can launch it. Okay, that's one side of competition. Second side is more stringent. You have to make both the rocket as well as the CANSAT, and it has to meet the criteria. Whatever we have done is 1,000 meter, but still higher things are there. Okay. Now coming to the basics. Now let us go to the basics because Tsiolkovsky is rocket equation is the fundamental to rocketry, and this equation is applicable to for both solid, liquid, and other one cryo also, but not for electric propulsion, as obviously. And the m0 is the initial mass of it. Okay, and final mass is mf. Originally is m0. So adding more, propellant, you can see it's a natural log, so there's no use. So since it is natural log, say 5,000 to 6,000, maybe by changing m0 by mf, the ratio, by improving the ratio, you won't get, maybe even if the ratio is becoming double, that you won't get the double effect. Being a natural logarithm is acting on that. So here, what is V? V is the exit velocity. What is exit velocity? Exit velocity, the nozzle through which the exit, what you call the gaseous products are coming out. Okay, so that is V and delta V. And what in earlier also I was telling, delta V is the most important as far as the rocket is concerned. How much energy we can give to the payload. So payload needs some energy to put it into certain orbits. But the orbits will come later. So what is now? You can see the bottom side, ISP. That is a specific impulse. Specific impulse is the way by which we compare different type of engines like solid or liquid, or even liquid itself, different propellant combination, or cryogenic, or what may be. So ISP is like you can say that let us compare like a calorific value of a fuel like a kerosene, petrol, or in diesel. We know that calorific value is something different, and we know that latest combination of alcohol with petrol is maybe because alcohol calorific value will be less, so the combination is likely to give less energy. So that is the concern expressed by some people. Okay, so ISP is the fundamental element which is used for comparing the different type of engines or propellant system, rather propellant system. So its a unit is S. The definition, and sorry, the total equation is not shown here, but it's a specific impulse. Its unit is S. Now coming to why rocket matters. So its primary objective is to have the primary objective is to enable orbit insertion, and of course conversion of energy. I must achieve our most important requirement is precise delta V. That is more important. And ISP is a corollary of that. And multi-stage, okay, multi-stage anyway, we will come later. Or already we have seen the different vehicles with multi-stages. The basic physics also, let us look into it. One is definitely the Newton's laws, where we cannot set apart Newton from any of these things. And gravity defines orbital mechanics and Kepler's laws. We are going to see something detail about that. And all of you are, studied this thing in your school days and +1, +2. So we are not going to dwell on it. But however, you can see these three equations are very, very much vital. And third one is definitely acting on, as a direct action on the rocketry. Kepler's thing also. This also you have already covered in your school days. Here, the first law of orbits, the planets move in elliptical orbit. Okay, but all of you know that. And second one, you can see that that T1 is equal to T2. When T1 becomes T2, A1 will become A2. You can see the area difference now. But once T1 and T2 are one and the same, the line joining a planet and the sun sweeps up equal areas during equal intervals of time. So that when T1 is equal to 2, the area will be same. It has got its own application, and we are not going to discuss in this class today. And third law is also like that only. The period is proportional to cube root of A. A is the semi-major axis of the ellipse. And the two-body problem, so the orbital mechanics, because Kepler has contributed a lot in this, deals with motion of one body under the gravitational influence of another. Always we need it. In fact, when we have a sun-Earth system and moon-Earth systems, all these equations these theories are widely used for mission planning. The simplified two-body model assume point masses and neglect non-gravitational forces. You can see the different types of orbit: circular, elliptical, and medium, MEO, and polar, and all these things. Now, the orbital mechanics, of course, circular orbit is one thing, and elliptical orbit, and escape velocity and LEO velocity. And you can see the velocity, LEO velocity, 7.8 kilometers per second. But the orbit is going up and up. What way the velocity moves? Anyway, this is not an interactive session, but I will answer to it. Okay. As altitude increases, the orbital velocity decreases. This is one thing you can see this. 200 kilometers, you need to suppose if you are satellite, many people are using their CubeSat and all. Many students like you, all institutions are sending to low Earth orbit satellites like 400 kilometers and so on, but need to have a circular velocity. Why? You know that otherwise that fellow will be coming down at the earliest. Okay. Whereas in GEO, it is you need hardly 3 kilometers per second is the velocity you have to give. And the equation is that you can see the R is in the denominator. Okay. And R goes up and up, the circular orbital velocity will come down, and mu is a constant. So now we have seen a model rocket. Now let us see the forces acting on a rocket. This is a simple figure. The complexities are not drawn into this. What is the weight? Okay, weight, as you know, it's acting always from the CG. And lift is the other one. Lift, in fact, the influence is slightly less in this case. And the thrust, definitely the thrust is required. And the balancing thing only is pushing the rocket ahead. So here, this is model rocketry. Anyway, the Sandeep Ji is attending this. He is, I mean, one of the mentor of, is a mentor of a big rocket team. The CG must be ahead of CP. That we will show in the next figure. In the same figure itself, it is given. So because it has to, I mean, put back the rocket in the right direction. It has to give a restoring moment. So the CP, what is CP? CG, you know, CG is the whole mass. Suppose however big a body, we assume that the entire body mass is acting at a single point. Same way, CP is the aerodynamic coefficient. It's a center of pressure. Center of pressure means where all the aerodynamic forces supposed to act. Same way like CG. We assume that is acting through a single point. So CP is the center of pressure, and the next one is center of gravity. So these 2 points are very, very critical, and CG should always be up in the model rocketry. That is one of the criteria. And in fact, the caliber and all not discussed in this talk. And you can see the weathercocking, how the wind is acting on a model rocket, and how the CG on the upside is able to help it in the right direction. But still, if it is more, there can be some tilting can happen due to weathercocking. Why? Because model rocket is not a controlled rocket. We will come to that point later. So when you are, why we are telling the students have to undergo this model rocketry lessons are, at least the fundamentals of aerodynamics and basic design, and at least the integration part of it, electrical and mechanical integration, wind, telemetry, and all the fundas will be very easily, and using practical classes, you'll be able to understand. And also, in addition to that, definitely the superb joy of a successful mission that we can really experience, because since we have seen a competition, how the students are enjoying that. And sounding rockets. The sounding rockets, of course, whatever ISRO has, as a space agency has started sounding rockets in the early 60s. And sounding means only for making some atmospheric experience, some measurement. So these are not suborbital flights, around maybe 100 kilometers or 150 kilometers is going. And same way like model rocket, these are uncontrolled and unguided. Okay, there's no control system, no guidance, and of course it has got a fin. And fin is a very, very important as far as a model rocket or any rocket. At least in the case of model rocket also, that is for it is controlling CP. So fin and its shape and its area are important. So these things will be understanding once you are undergoing a model rocketry experience. So then spinning. So this sounding rocket is a very small, compared to vehicles, it's a very small rocket. Mostly for measurement payloads are being sent for that. And these are the RH means Rohini. So Rohini 560 is 560 millimeters. Okay. The thruster, the booster, the bottom one. But the bottom one is 560. This is totally 560. Next one is a 560 plus above that. You can see the RH 300. That is 300 millimeters. The top one, the 2-stage. And it is fin stabilized. Now coming to the important things like a space mission and its objectives. So far we have seen the elementary things about a rocket. Now we have to go for a space transportation system that is about big launch vehicles. Here I'm trying to give you an overview only. And in that, when a space transportation system, like a surface transportation, you have a train is there, you have buses are there, your cars are there. So in this case also, it has got some payloads, and like a goods train. Okay, you have payloads here, or you can carry human beings. But there's a difference. There's a difference between space transportation and the surface transportation. We are going to see that. But no, we have this is one sort of classification of missions: Earth orbit missions and deep space missions and interplanetary and interstellar missions. So it means slightly a large scale. Further you can go to the minute level also. So when you design a mission design, when you want to make a launch vehicle, when you want to make a launch vehicle, the planning is most important. The first thing you have to see, you are a startup. Assume that you are a startup. What is your mission? Your mission is what is your payload? Your payload, assume you want to put 100 kilogram or say 50 kilogram, and you have an orbit. Okay, what should be your orbit altitude? Say 100 kilogram. Sorry, 100 kilometers, or say 200 kilometers. Then what should be your? Then you are coming to next level. Like anyway, this is I'm trying to show the trajectory in Sriharikota. This is a gravity turn the vehicle is taking. Now coming to vehicle configuration. So this is the burning issue when the trajectory deciding is a burning issue when a launch vehicle is getting designed, especially when countries like India. The vehicle configuration, selecting the appropriate launch model, stages, engines, propellants, and the mission sequencing. Mission sequencing means from the firing onwards, when the stages have to separate, then each stage has to separate, and similarly when the payload fairing has to separate. And these are the exact timing and cutoff, ignition, everything consigned. This is mission sequencing. And normally this part is done by the aeronautical engineers, and with the support of control system engineers like those who studied some electronics and communication or something like. And then EEE people, okay, those people are having scope in this area. And of course, mechanical engineers are having wide scope because the whole manufacturing, everything they have to take care of. Whatever you're seeing physically on this one is a contribution by mechanical. Then some sort of structural engineers are there. Those are studied in, have specialization in structural engineering, and chemical, of course, the propulsion part. So all branches are required. So, of course, computer people, they are everywhere. The software is the most important part. These are the types of orbit we have already discussed, and sun synchronous orbit. Okay. So here, the orbital plane maintains constant orientation related to sun throughout. Okay. So the satellite passes. So this is the polar inclination. Polar inclination. Why? Because why we are going for the sun synchronous orbit is in certain a specific location, specific time, the satellite will be watching us. Just get the coverage. Say 9 to 11, you want to have a specific area to be, covered using a satellite. It's possible only through this, using such an orbit. And launch vehicle systems. Okay, major systems. We are coming to that, and criteria of selection of material and fabrication technologies. And coming to the manufacturing part of it. Manufacturing is, in fact, what when you say design means design doesn't mean that the mechanical part of it. Design of the structural engineering is there involved in that. Then we have electronics, avionics. We call it avionics, aviation electronics or avionics. Electronics is involved. Then electrical integration is there. So all these things are, it's a something like a system engineering. So number of iterations. And conceptual and the preliminary. So the design stage is given here: conceptual, preliminary, critical design reviews, and finally we reach an optimal design. Number of iterations. And propulsion system, we have to choose which is ideal. And of course, economies also matters. And electric is not up to the. Currently it is used for satellite area more, not come to the launch vehicle area. Then coming to the manufacturing part, only give you an idea about it, because they say, you may be in the 6th or 7th semesters, you'll be getting an idea about it. So first one, when you design something, whatever may be the system, design for manufacturing is very, very important, whether it is an electrical system or a mechanical system or a structural system. So the important things are like choice of material, manufacturability, and the process. You can choose multiple process. Same item can be made by welding or by, even nowadays 3D printing is there, and by casting, or so many methods are there, and which one you have to choose, or by simple fastening. So this is also very, very important. That is ensuring the manufacturability and economic process selection and cost effectiveness. And the last point is also very important, because testing and qualification, aerospace, it is not the least point, it's the very most important point. And coming to the materials, of course, materials, I'm giving a brief about that, because when you choose a material, it is a critical engineering decision. One is structural integrity, performance, reliability, and above all, in India, we have availability is very, very important, because India is a country still be importing a lot of aerospace grade materials, even parts, electronic parts, and so many chips and all. So then we have import restrictions put by certain countries. Still, it is there. So cost effectiveness is very important. So availability is there, and availability, another important point which startup is facing, that the minimum order quantity. You have to buy minimum things, minimum, like when somebody is delivering, they may charge your online portal, they may charge. If it is less, they may charge your handling, your transportation charges or service charge, they may charge. If your order is slightly above that amount, your free delivery you'll be getting, or delivery charges you have to pay. Same way. It's not something same way, they will not deliver at all in this case. Minimum order quantity is there, because for them producing a small quantity is not viable, whereas they have their own reasons. Coming to the primary material selection, being a space environment from very minus to very plus, it has to go. And the certain propulsion items are 2500 Kelvin or even 3000 Kelvin test to phase in this. When you go to space, it will be minus 150 degrees Celsius will be there. So we need to have material which is working in all conditions, and at the same time, not only working, it has to maintain its properties. So that's why this slide is very, very important. Structural integrity it has to maintain. These are the important points we have to take care when it's not a small job, because selection of material is a very critical job. We have metallurgists are there, material scientists are there. So they're also working on this. These are some of the alloys we are using by ISRO's launch vehicle, and 15CD V6, 0.15% carbon, and chrome, molybdenum, vanadium steel, and a variety of aluminum alloys and titanium alloys we are using it. Okay. And titanium is very much important, especially cryogenic stages and even semi-cryogenic stages. And fortunately, these titanium alloys we have indigenized to a great extent through Midhani, Misra Dhatu Nigam in Andhra Pradesh. In Hyderabad. Okay, it comes into Telangana, it seems now. Okay, in Telangana. And the things are developed by ISRO in-house material science, reverse engineering, and it is getting produced by our own facilities. Whereas still some of the aluminum alloys are getting imported. And these are some of the exotic materials, and this we need for even Gaganyaan missions also, human-rigged missions. inconel, pneumonic, vascular alloy, haste alloy, niobium based. And monocrystal alloys are very important. You might have read in recent newspapers or LinkedIn, and the turbine blades of jet engines and all, monocrystal alloys they are using. They have to use. Okay, it's currently we are not producing in India, but at least research level we have accomplished monocrystal alloys. We can make it in that is current condition. You can see the numbers 2014, 2218, 7075, all these things. Okay, each one is property is different, usage is different, and okay. Next is some people are interested in satellite. That's what I'm telling about satellite. These are the copper beryllium, and this is with lead. Okay, lead is something is added, but lead not an advisable content. Without lead also we can use it. No lead, copper beryllium is also used. So this is used for very high frequency antennas. This is not only for CubeSat. This is used for regular satellites also. And composites anyway, it's a very interesting material, but we are using in tankages. We are using in Skyroot also is using that motor case is using it. Skyroot is a startup, and launching is going to happen next month, sorry, July. So composites, the same way when you don't get carried away by composite. Composites only a name of, it's a generic name. We have polymer metrics, metal metrics, ceramic metrics, and carbon metrics. Composites are there. And coming to the LVM3 launch vehicle, why this vehicle is chosen means this is having all the three types of propulsion systems. S200 is having solid. It is STPP ammonium perchlorate is being used, and L110 is and that is an N204, and U means UDMH tanks are there. That's also L110 is there are double Vigas engines used inside the stage. And C25 is a cryogenic stage, and top one is a payload fairing. And coming to hardware, broad classification. So you can see earlier we have described about the total configuration of a launch vehicle, LVM3. So we have rocket motor cases and everything contained in this vehicle, and we are going one by one. First is solid motors. So the solid motor, in fact, as far as ISRO is concerned, ISRO's main strength is in solid motors right from the beginning. So that's why in all launch vehicles we are giving much importance to solid vehicles, because it gives first of all ease of manufacturing, testing, less complex, and as far as ISRO is concerned, we have plenty of manufacturing suppliers are available, and materials are also available. So in M250 is the marine. So M250 is the marine steel we are using for this boosters in PSLV, GSLV Mark II, and GSLV Mark III. Why we are using this M250 marine steel? In fact, it is got American heritage, but now it is 100% indigenized, and it's a high strength material of the order of 1,800 megapascal. Is the ultimate tensile strength, or we call it UTS of this material. This flow chart shows how a simple, what you see is a simple motor case, a simple cylinder. How it is getting made? It's made out of number of sheets and rolling sheets and plates. It's not okay. Plate, I can say it is around 7.8 millimeter, so we can call it plates. Then long seam welding. Then you have those things we will see now, and these are all the different stages we are passing through. And these are the basic technologies, welding technologies we are using. And probably you might have studied, some of you are in the mechanical engineering, might have studied all these things in their workshop technology or production technology. And these are the furnaces over which the cylinders are getting heat treated, because heat treatment is for the sake of non-mechanical engineers, I will say explain this is a thermal processing. And like Italy is getting its property only when it's getting cooked. Okay, in the other stage, whether Italy or chapati, it has getting, or any majority, not majority, almost all food items is undergoing some thermal process. So same way, the metallic material also has to undergo thermal process to get the desirable or intended properties which the designer is looking for. It has to meet the purpose. So for the desirable properties, we actually put the chapati on a pan, and we are making it. Put it this way, that way not be cooking it. Okay. Same way, you are putting in a furnace. You take some time for the your rice to get cooked or get cooked and all. Same way, here also the process needs specific times, specific hours. The hours may vary from 30 minutes in some cases, even some cases maybe 24 hours, even some cases 48 hours, depending upon the material and type of process. We are and also as I was telling, the type of properties. Say from the same material, undergoing different thermal process, using different parameters, you can alter the properties. And of course, the manufacturing process, this is something fundamental and elementary thing. We will go to the next one. This is a figure I've taken from NASA. It's a very simple model of a motor. You can see the propellant getting filled there. You can see that's a cylindrical grain we have shown here, but need not be cylindrical. Sorry, this is a star grain. Also, it's a star grain. That's on the left hand side is star. Okay, I'm sorry, it is a star grain. So you can see the section of that, and so the propellant has to burn, and you can see the nozzle here. First, near to the motor case, the cylindrical portion of the motor case, and the motor case is you can see the convergent part of the the dome, the curved part. No, the right hand side, the curved part of the motor case is called the dome. Connected to the dome, you can see the convergent part. There is a cone which is tapering towards the right, tapering down, and you can see the straight portion, that is throat, and the divergent portion, that is tapering to enlarging portion. So energy conversion happening, and the Mach numbers increases from Mach 1, 2, and Mach 3, Mach 4, Mach 5, and all. Okay. And this is what we are calling the exit velocity. We have seen the Slowski equation like V. Now coming to the structures, because we have a multi-stage rockets we are using. Model rocketry itself is, though we can say it's a multi-stage, not to that extent, because it's all like a body tube, and inside the body tube, in the bottom portion, again you are keeping the motor and then the fins, and then we have the other patch tube and other things. Whereas in this case, we need structures. We will show anyway the full launch vehicle you might have seen. I have not specifically told about the structure location, because the stages, when the liquid stage to cryo stage, there is structures are there. And you can see the strap-on motors on either side. There are also structures are available. After the motor, rocket motor, there is a nose cone portion you might have seen in the launch vehicle. There is also in those areas there are 2-3 structures are sitting. The structures is normally we are making of aluminum alloys, because of the the strength to weight ratio is better. Not using steel. Why steel is using in motor cases, I have already answered. It has to take that much pressure. It has to make, so the thrust will be high. So if at all we are using aluminum, we have to go for a very high thickness. So we are going for a high strength materials. So the basic equation PD by 2T for a pressure vessel. Okay. So the T comes the thickness. PD by 2T is the equation governing what do you call the pressure vessel. A solid motor is a pressure vessel itself. Motor case, I'm telling you. Motor case is a pressure vessel, not the motor inside which we are filling the propellant. Now, safe life design is something which is a specific operational lifespan. We assume we design for example, your TV, all these things are some for some design for some years of life, even your own bulb and all. Whereas fail safe is something which we are using it where redundancies put into, and normally in household items we are not going for redundancy, triple redundancy, all these things. But in aerospace systems, these things are mandatory. So that means if one is failing, and another has to act. And for Gaganyaan, we are going up to quadruple redundancy. That is 4. If one is failing, then 2, then that is failing 3, and then 4. Quadruple where possible, because redundancy also, practicing redundancy in a system depends upon the type of system itself. May not be possible in all systems. So there is also another criteria. Now coming to damage tolerant design, this is something for pressure vessel like motor cases and all, and even structures also. Assume that there's a crack. So we can estimate how much time taken in even the specific stressed condition itself. In the stressed condition or in the usage condition itself, how much time the flaw will take to reach a level so that it will lead to catastrophic failure. So that is damage tolerant. When the damage is existing, however, it will not fail. So these are the classification of aerospace structures, the monocoques, main monocoque, and isogrid and orthogrid and all. At this level, you may not be able to understand, but we are going to see some of the times, some of the items in this figure. Here also, like in the flow chart, I have used here the manufacturing stages of a structure. But concept of a model, a solid rocket, motor case, or a structure is different. In a structural design, we extensively use our metallic materials. This figure shows the principle of a liquid engine. Got a fuel oxidizer, whereas in a solid rocket, we are mixing that and we are casting it as a single thing. Okay. And as usual, there is a combustion chamber and we have a nozzle. On the left-hand side, we are seeing the LVM3 L110 stage. We heard the video, the L110 stage separated here. Somebody's announcing. Say it's a twin Vigas engine. You can see the 2 nozzles are there. Inside, there are 2 engines are there. On the right-hand side, you are seeing the same engine on how the engine looks like without the assembly. The engine as such, we are seeing it. The top side, you can see the combustion chamber, and the bottom side, you are seeing the nozzle part of it. And this is a very complex engine. We are using it. This is only an overall view I will give you. These are some of the fasteners. And sensors I have already shown the figure of certain measurements. And you can see that we need the requirement of instrumentation engineers here. That's what another branch of engineering, instrumentation and control system. And a lot of, it's only that in classification, but number of sensors are very large. And this is very important point. This is a quality assurance part of it, quality assurance. And though it is an unspoken thing, it is hidden each and every part of the slides I have shown. Design verification analysis. There's a, whereas in ISRO, the quality assurance team participate in all activities. By definition itself, the quality assurance has to take care of from design to the product reaches the customer's hand. So engineering, drawing, materials and manufacturing process, the inspection, quality control, storage, handling, transportation. And the storage, we have a big, manuals are available, handling drawings and manuals are available, and transportation also, criticalities are there, especially payload fairing of 11-meter and 5-meter diameter taken from Bangalore, or now it's currently made in Coimbatore also, to Sriharikota. We have a pilot worker in the front and the back. We have to inform the respective police stations or district authorities the system is coming, and most of the journey will be in the night, because in India we face all these issues, logistic issues. So because the manufacturer centers are slightly away from the launch port. Now we are coming to another interesting part of it. That is, so far we have dealt with what our National Space Agency is doing, ISRO, and now we are coming to the space ecosystem, mentored and inspired by NewSpace, International Space Promotion and Authorization Center. You can see that the new space technology trends and new space ecosystem here. And if you look at the business of space, this launch vehicle, whatever you are shown, anyway, you need a vehicle to take the spacecraft to the designed or determined or pre-designed orbit. Now the launch, the launch, whereas the satellite or SATCOM business is around 40 to 50%, other only 60%. So 2,500 satellites to be launched on average every year, and 7 satellites a day. So I think the students community sitting here, please note this point. There's a good opportunity once you're passing out in this field. And part of the 2047 vision, in fact, you'll go to that reusable launchers in Indian Orbital Station, lunar mining station missions, and global satellite manufacturing leader. Okay, we can have, because we have 140 crores of people, and we have bright youngsters like you, we can go, we can take the leadership. And this is one reusable launcher. Let us see a small video of it. Okay, this is a, anyway, you may be knowing the answer. Why we have used, thanks to Indian Air Force, why we used a helicopter? The answer, obviously, it doesn't have a propulsion system. Okay. So we discussed this for a different purpose. That's why we have used that. Now, this is our, recently we have already partnered with the space station idea was there with us, but of course the technology is quite complex. we have a, when with the Prime Minister has already had a meeting with when the President of Russia came. There's an agreement is already put up with Russia to partnership with this. And this is something like a nuclear thermal propulsion. This is another area, because for interstellar mission or interplanetary mission or deep space transfer vehicle, because we need to have there's a constraint when we are using the normal propellant, like even electric propulsion also, it may have its own restrictions. So we have, people are developing nuclear thermal propulsion, and not only Russia, even China as well as Russia. Russia also, this is American, sorry, this is Americans, and along with the Russia and China also successfully made at least the pilot models. And these are all the electric propulsion, the next generation, and currently in use. This all, and again, this is AFMPD, is a magnetoplasma dynamic thrusters. This is another technology. But here, okay, we need to use xenon or krypton. Normally, standard electric propulsion uses xenon or krypton. There are actually very rare gases, but here they claim we can use argon, ammonia. These are all available. So that is the difference between this engine and a normal electric propulsion, where we are using xenon and krypton. These are even some, I think, 1 or 2 Indian startups also trying to develop this. In Europe also, they're trying to develop this. This is about the previous one. Okay. Now coming to moon colonization. We need to have plans for that, but but the constraints, we are coming to that. We need to solve these issues. Whenever people are telling some ideas, they never say they always say the pros of it. They are never tell about the cons. Even if you going for a shop, also the marketing fellow will tell you the pros. Here, cons are radiation, dust abrasion, and 14-day night. If you are going to live in moon, it's a 14-day night, and water extraction and construction material and many more. And so many more things are there. So currently, what many countries are planning is sending humanoids and robot first. Okay, so these are some constraints but definitely the lunar moon can be explored for certain rare minerals or rare elements. That idea is still, that idea is currently working on by major spacefaring nations, India too, although at a humble beginning. And let us see what our youngsters are doing now. New propulsion technologies, metal ox, nuclear thermal propulsion, ion thrusters, solar sails, and fusion drive. And the Skyroot, anyway, the launch hopefully come next month, July, first or second week. The mission readiness reviews are going on. And initially, they will be sending a small satellite payload, and around say 350 kilometers, something like that. And this is a very happiest moment for every Indian, because Galaxy is an achievement. Galaxy, though it has gone in SpaceX, achievement is great. They have optometry as well as synthetic aperture radar. The two type, it's a merger. They have used merged these two configurations of or the two sensors. The two sensors output can be they are combining, and it is synthesizing and getting the final pictures. It is in fact, and also it is a history. They made a history, first in the world. Okay, so these things are actually the happiest moment for every Indian. Our youngsters are doing well in this field, and you can see some of the good startups, and hope at least some of your names also will fall under this in future. Pixxel, Skyroot, Agnikul, Satsua, and Digantra Research, and Bellatrix, and Dhruva Space is also here from Hyderabad. And Assista name is not here. Assista is also there. They're also making satellites. And there is one big company, I don't know, but not coming under startup and technology, Bangalore based. They are going for a launch vehicle also. They are going to have, outside ISRO probably the largest one. And they're making bigger satellites also. So the space ecosystem in the private domain is growing like anything. And space economy is 44 billion is our target. Probably you might have heard through LinkedIn or through media. So in space enabled private sector reforms. Okay, of course, in space is doing that. And thank you so much. And we will stop with a small verse from Gita.
Subscribe now